Okay, let's jump right into this explainer. Today we're exploring a pretty profound collision between two entirely opposite worlds. On one side, we have traditional, strictly rigid computer science. On the other, the modern, highly unpredictable, somewhat messy world of artificial intelligence. We're going to see how a probabilistic AI actually managed to completely floor one of the most uncompromising mathematical minds of our time. It's an incredible story of two totally different computing paradigms smashing together, and honestly, the results have left even the most seasoned experts absolutely speechless. To really kick things off, you've got to hear this stunning admission from Donald Knuth. Now, if you're into computer science, you absolutely know Knuth. He is the legendary pioneer, the guy who wrote The Art of Computer Programming. Well, he recently admitted that AI, and I quote, greatly surprised him for the very first time, bringing him actual, genuine joy. And to truly grasp why a quote like this coming from Donald Knuth is so monumental, we kind of need to look at the world he built and the unbelievably strict standards he's maintained for over 50 years. Section 1. The Master of Algorithmic Rigor. So to understand why this AI breakthrough was such a shock, we have to establish Knuth's absolute dedication to mathematical precision. In his world, ambiguity is literally the ultimate enemy. He formalizes perfection. Just take a look at this mathematical tree. This brilliantly illustrates his entire mindset. Knuth maps out traditional algorithms with deterministic perfection. See how the branches are designed to rigorously minimize the number of multiplications needed? It's basically like mapping out the absolute most efficient driving route where you are guaranteed to never hit a single red light, calculated down to the millimeter. It's a closed, perfect system. Every branch, every operation guarantees a specific outcome. There is absolutely zero room for guessing here.
I mean, the guy is so notoriously rigorous that while he was developing the text typesetting system, he painstakingly categorized every single programming error he ever made into 15 specific types. An A for an algorithm awry, a B for a mental blunder, an S for a subtle surprise from some complex interaction. He logged thousands of these things. He essentially treated his own human fallibility with the same surgical, data-driven exactness he applied to his code. If he made a mistake, he didn't just fix it and move on. He mathematically cataloged it to make absolutely sure it never happened again.
He even designed a simulator for the MMX pipeline, a theoretical computer architecture where the flow of computational traffic is meticulously synchronized down to exact 100 nanocentury intervals, which, by the way, a nanocentury is a wonderfully weird way to measure time. But think about that level of control. It's like a high-tech assembly line where every independent functional unit processes instructions in this perfectly orchestrated, mechanical dance without a single microsecond of deviation.
Section 2. The floating point problem. But here's the catch. Even in classical computing, achieving that kind of absolute accuracy is a constant battle.
This brings us to what Knuth calls the credibility gap. This happens when you try to represent real, continuous numbers inside a finite digital machine. Standard 64-bit floating-point math can actually produce highly misleading results entirely silently. Basically, computers use finite precision, so they round off numbers. It's kind of like trying to divide a pie into exact thirds using a pixelated knife. Eventually, those missing crumbs really add up. You could get an answer that looks perfectly legitimate, no error warnings at all, but because of accumulated rounding errors, it is completely wrong.
So how do they fix that? Well, to conquer this credibility gap, computer scientists pursue these hyper-rigid, hardware-level solutions, like high-radix online arithmetic. I know, it sounds super dense, but it's actually fascinating. It computes operations serially, reading the most significant digit first, like reading a number left to right, so you immediately know its massive scale. This ensures everything is perfectly accurate right at the microprocessor level. It's the ultimate classical computing mindset. If there's an error, just build a more robust, perfectly deterministic machine to eradicate it.
Right, let's move to Section 3, AI's messy, probabilistic mind. This is where things get really interesting, because AI works nothing like what we just talked about. Unlike the deterministic world where you have guaranteed accuracy, clear data paths, and predictable 100 nanosecond intervals, AI is fundamentally open-ended. In classical computing, you input X, you get Y, every single time. It's a guarantee. Generative AI, though, it relies on probabilities, weights, and billions of hidden connections. Instead of a guaranteed calculation, it operates much more like a really highly educated die roll. As researchers point out, AI operates on a messy conglomerate of heuristics. It's the exact philosophical opposite of Knuth's universe. It's not executing a flawless verified math tree, it's guessing based on immensely complex patterns drawn from massive datasets. For a pioneer like Knuth,
who spent his whole life wiping out ambiguity, this is usually seen as totally unreliable. How do you trust a machine that can't mathematically prove its own steps?
Which brings us to Section 4, the AI math breakthrough. Because recently, these two completely opposed paradigms collided over a brutally complex math problem.
So here was the challenge. Knuth had been stuck for weeks trying to find a general formula for directed Hamiltonian cycles. This requires intense combinatorial exactness. Think of it like trying to find the perfect route through a sprawling city map, where you have to visit every single intersection exactly once, and the roads keep changing based on complex odd-numbered rules. It's exactly the kind of rigid, formal puzzle that human brains usually have to just grind away at for years.
Then, he threw an anthropic hybrid reasoning model named Claude Opus 4.6 at the problem. See that massive 31? That is how many different iterative attempts the AI made to crack this. It didn't just spit out a magic guess or hallucinate a fast, wrong answer. It worked the problem over and over, refining its approach every single time.
And watching Claude's method evolve is mind-blowing. Instead of purely relying on dumb brute force search, it iterated. First, it explored angles and basic patterns. Then, a huge breakthrough. It stopped looking at the grid as a whole and intelligently grouped the points into layers. And finally, when rigid search methods failed, it essentially put on what Knuth called a mathematical thinking cap to author a specialized computer program specifically designed to solve this exact puzzle.
Now, Knuth being Knuth, he didn't just take the AI's word for it. He mathematically verified it. He provided a formal proof confirming that the AI's automated deduction successfully cracked the rules for every odd-numbered grid size they tested. Out of 760 possible Claude-like decompositions, the AI independently discovered one that worked flawlessly. This messy, probabilistic system solved a perfectly rigid problem.
Section 5. A new computing era. This is the moment that bridges the gap between probabilistic guessing and formal mathematical proof.
For a legendary skeptic and literal paragon of rigor like Donald Knuth to celebrate this as a dramatic advance in creative problem-solving, that signals a massive paradigm shift. As he says himself, he's not an AI hype guy, yet this messy conglomerate of heuristics managed to write a specialized program that got him unstuck. He even admitted he might have to completely revise his opinions on generative AI.
So I want to leave you with this. Some people argue AI is just a high-tech tool, right? No more intimidating than the calculator app on your phone. But if a messy, probabilistic system can shock the ultimate master of algorithmic rigor with pure creative deduction, are we really just building better tools? Or are we actually witnessing the birth of a totally new mind space? Think about that as you watch where this incredible technology goes next. Thanks for joining me on this explainer.